Okay, so we have a different kind of function here, and square root of x squared minus 2. And there's a few things that you could try to think about the nature of it. You could try graphing it. If you were going to graph it, you'd have to, I think, sort of come up with different values of x. And thank you. And maybe think about the properties, the domain, the range. The domain is going to be a big one. How does it compare to y equals x, square root of x minus 2? So one thing that jumps out to me when I think about the square root function is it has a very important domain, right? Because when you take a square root, you don't get negative answers. So that has a horizontal shift but no vertical shift, right? So you're never going to have any negative y values. And if the radicand of the square root, which means x minus 2, right? So I would think about this. If x minus 2 is less than 0, I'm not going to get an answer because I'm going to be taking the square root of a negative number, which means if x is less than 2, right? So if x is 1, 1 minus 2 is negative 1, you get a negative radicand, and so it doesn't make any sense. And that's why the domain is what it is, right? So that's interesting. So how do we do the same thing, but for this function? That's something that I would think about. So that when you start plugging in numbers, you would notice. So let's say I put in, I don't know, 5. 5 squared is 25, minus 2 is 23. The square root of 23 is whatever, like it's just under 5. That's not important. It exists. What if I do 2? 2 squared is 4. 4 minus 2 is 2, so that works. Brandon, what do you think?
I was wondering for the domain that x is less than 2, it can be less than 2, it's still true.
It can be less than 2, it's still true for this one?
Yeah.
Yes, yeah. Right? It can be. What can't it be, though? What if I made it 1? 1 squared is 1. 1 minus 2 is negative 1. That won't work. Somewhere between 1 and 2, you end up with, well, think about it. X squared minus 2 has to be greater than 0. So x squared has to be greater than 2, and then x has to be greater than plus or minus the square root of 2. Something along those lines, right? And if we think about it, if I put 0 in, it doesn't make sense, but we didn't talk about this yet. What if I put negative 2 in? Because normally with the square root sign, you can't do that. But when I put negative 2 in for x, square it, you still get positive 4. So you still get a viable answer. So here's the graph of x squared. This will make sense in a minute why I have this. Here's the graph of the square root of x minus 2. Let's take a look at what the graph of x squared minus 2 looks like. So this is called the composition function because it's what we call the composition, which is a form of combination, which we're doing combining functions, combinations of functions. It's called the composition of functions because it has one function, x squared, inside another function, the square root of x minus 2. That's what makes it a composition of functions. And so when I look at, I can think about the nature of x squared and what it's like, and then think about the nature of the square root of x minus 2 and what it's like. And I have to combine the nature of those two in an interesting and unique way to understand what my new graph is like. And so that exercise, the most important thing I think about this exercise that we've done here is thinking about domain. And my domain of the overall function, in this case f of x, has something to do with the output of x squared, right? The output of x squared. We'll come back to that in a minute, and it'll make more sense a little bit later. Okay, so we saw the graph of it here in GeoGebra, so I won't graph it now. We'll just leave that. Okay, good. So here we go. Let's talk about what a composition of function actually is. So we've got two functions. F at x is just linear, 3x plus 1. G at x is x squared minus 5, so it's a quadratic. Once again, this is great review of a lot of the stuff that we've done in this unit coming up for the exam. While you're doing the practice for this, I think that you will have to strain your brain and your memory to think back, oh, what is the domain of that kind of, what does that look like again? I can't remember. But that's a worthwhile exercise to do. Like, it's important for this unit, but it's really important for the final exam. So we're going to revisit a bunch of things that we haven't seen in a long time. It is worthwhile to figure that stuff out. However you go about doing it, look back in your notes or talk to somebody or ask or graph it with technology to remember what the graph looks like whatever it is. This is great review, and don't just bypass it thinking, I probably don't actually need to know this. Yeah, you do, especially for this, but also for the exam. Okay, so we've got these two functions. Determine f at g at x. That is one of the two notations we use for composition of functions. So you'll see this one used quite often. So we could do it the long way, which would be 3. So I'm going to sub, like this is like f at 10. I would take 10 and sub it in for x. But it's f at g at x, so it's like f at x squared minus 5, right? Which is 3 bracket plus 1. What do I sub in for x? X squared minus 5, g at x. X squared minus 5. And again, in this case, I can do some simplification. You may or may not need to, depending on what you have to do next. But this is 3x squared minus 15 plus 1, so 3x squared minus 14. Okay. The other notation that we use is this circle. And so there's a whole bunch of different ways you can say it. You can say G composed with F, or you can say G at F, or G of F, or G round F, or G circle F. There's all these different ways of saying it. Not all that important that you know all of them, but for some reason there's a whole bunch of different ways of saying it. Okay, so this is the same thing. So, and this notation means G at F at X. That's what it means, which is G at 3x plus 1. So I take my x squared minus 5, and I put the function f in there. So 3x plus 1. So 3x plus 1 all squared is 9x squared plus 6x plus 1 minus 5. We get 9x squared plus 6x minus 4. Good? I don't know. Might be able to. You could check the discriminant, see if it's factorable. B squared minus 4ac, that's what I would do if you had to factor it. I don't know that we have to. You could complete the square to graph it, although that's going to be a bit messy because you're going to have to divide by 9. So anyway, but you know, in this case, that's all you have to do is find an expression for it. So we're done. F at g at 1. This is interesting because it shows us what I was talking a little bit about earlier, is the output of G is the input of F. Okay? The output of G is the input of F. So one thing I could do here is F at G at 1 is this function here, right? So like F at G at X, or F composed with G, or F of G, is that expression there. So I could sub 1 into that. That's one of the things we could do. So this equals 3 times 1 squared minus 14. So that's 3 minus 14, which is negative 11. But this should be the same as G at 1, which is 1 squared minus 5, which is negative 4. And if I do f at -4, output of g at the value of 1 becomes the input of f. So 3 times -4 plus 1, which is -12 plus 1, which is -11, right? So you better get the same thing. That's what makes sense. But we have an expression for it now, so we don't have to do it in 2 steps. We can do it in 1 step. You know, that's algebra, right? That's the power of algebra. Okay, so try the next one yourself. You don't have to do it both ways. Just a nice demonstration. Thinking about it will be important to not just do the algebra, but understand the output of G when I input 1 into G is the input for F. But then the output of F is the output of the whole composition function, right? Like that's the overall output. What was the overall input? 1. I put in 1, I got out 11. Okay, anyway, so try D. -4. Math was pretty easy there. And again, if you do it in 2 steps, you'd get the same answer. Pretty straightforward. A little bit of algebra going on in some places. Again, it's a good warm-up, not hard stuff, grade 10 stuff, but a nice refresher of some of the, like there's a couple of questions in the practice that are good practice for some of the stuff we did earlier in some of the earlier units. Okay, example 2. Here's where it starts to get interesting. Determine the domain and range of each of the following. Okay, so domain for this one, x is an element of the real numbers such that x is greater than or equal to 0, right? There's nothing weird going on there. Range, y is an element of the real numbers such that y is greater than or equal to 0. Somebody help me out with domain and range for g at x. What are the transformations? What's happening? What does it look like? You might want to sketch it, think about it, something like that. Again, good review. What's happening here? Anybody? Okay, so domain x can be anything. Exponential function, right? And what about range?
Range must be less than 4
And can you explain why?
because it's usually like above the 0.
Mm-hmm.
Yeah, y equals 0.
Mhm.
But then it's been flipped and then it's raised up 4.
Good. So y is less than, not less than or equal to, less than 4. It has an asymptote at 4, right? It usually has a horizontal asymptote at 0. Because when you take the exponent of something, you never get 0, right? Whether it's negative or positive. Okay, so f of g. Again, this is like f at g at x. So what would the equation look like? It doesn't ask us to do that, but we can write it down anyway. So that's the square root of negative 2x plus 4. So let's think about this. The input of a square root function, the radicand, has to be positive. When will that value be positive? That's what we're asking. And then what kind of output are you going to get? This is going to be my range. What do you think?
So it is odd and it's a great number. It would be invalid.
Say that again.
If it's odd and it's a great number.
Odd?
Yeah, like if the exponent is odd.
Oh, okay. Oh, it's not, the negative sign's not in brackets though, right? The negative sign's out front. So you're on the right track, but hold on, think about that again a little bit more. Okay, so let's think about this a little bit. So we've got, what was the first one? Square root of x. And the other one was negative 2 to the x plus 4. Yeah. So there's those two functions. Okay, square root of x, no transformations. Again, this is the exponential function, but it's got a reflection in the x-axis, and it's been shifted up 4. So when will, what is the domain of the composition of those two functions?
X is greater than 0.
X is greater than 0? Why do you say that?
Oh, greater than or equal to.
Greater than or equal to 0? Why do you say that?
Because if it's past that to the left, then the other one doesn't have any points. Yeah, then square root of x doesn't have any points.
Okay. Anybody want to add to that? Is that not what you expected? It's tricky. This stuff is a little bit tricky. So there's two ways that you can, or maybe different ways that you can think about this, I should say. Remember, what you're putting in is actually going in this case, to that function. What I get out of that has to be positive, because then it's going into that one. The radicand can't be negative. But that doesn't mean x can't be negative. If I put in a negative x and get a positive number here, which we already said, you get a lot of positive numbers, right? Then that would be fine. So if I put in negative 10, I get 2 1 over 2 to the 10, really, really small, negative of that, plus 4 is still a positive number. And we can see that in the graph. Right? If I put in negative 10, so up here, I do get a value for x. So what does it look like now, our domain? X is less than or equal to 2. And then what about our range? Possible outputs. Mm-hmm. Why do you say that? Very nice, but why do you say that?
Kind of flattened out.
Yeah? Okay, so you're doing that based on the graph? Okay, so think about this. This one might be a little bit easier. We'll talk about domain again in a minute. The biggest number I can get is 4. Less than 4, but let's say 4. Based on the range of G, that's the biggest output I'm going to get. My output of G is my input for F. So when I take the square root of 4, I get 2. So the biggest number I could possibly get is 2 or just under 2, right? And what's the lowest number that I can get when I take the square root of something? 0. Square root of 0 is 0. So my range is going to be y is an element of the real numbers such that 0 is less than or equal to y less than 2. Going back to the graph, take a look at the range. There's 2, okay? And the square root function, which is the green function, can be anything. X will go up forever. But there's a limitation on the input of the square root in this case. It'll never be above 4. So that impacts the range of the composition of the two functions. And then now let's go back and talk about domain again a little bit. What's the possible domain? What can I put in? What happens when I put in something like 2 to the, like x equals 3? What happens when I put in 3? I get 2 to the 3, which is 8. Negative 8 plus 4 is negative. So I can't take the square root of negative, so that doesn't make any sense. Okay, let's try the next one. Let's think about the next one. So what about G composed with F? G of F. So this is going to be negative 2 to the square root of x plus 4. Strange function. We'll take a look at the graph in a minute. What can I put into that function?
Any positive number.
Any positive number? what will I get out of that function? So whatever, when I put a positive number in, I'll get a positive number out. When I put a positive, any positive number in as the exponent, what's the nature of that function? So this is the kind of thinking that you need to go through to figure out domain and range. Okay, good. So domain, x is an element of the real numbers such that x is greater than or equal to 0, because it could be 0, right? Yep. And the range, y is an element of the real numbers such that, okay, so let's take a look at the graph. Whoa, it's orange. It's this orange one. Funky. So when I start putting in big numbers, the square root of 25 is 5. 2 to the 5 is 32. Negative 32 plus 4 gives me a big negative number. Right? And if I put in 0, you think about, I end up with 1, 2, 3. Okay, so back here, so the range is x, whoops, what's going on here? X is less than or equal to 3. Sorry, y. Okay, last example. This is actually pretty easy. Okay, so you're given the composition function, and you're supposed to find possible equations for f at x and g at x. This isn't about right or wrong answer because you could come up with lots of different possibilities. Anybody think of one possibility? For this? Brandon? Nice. Very good, right? So if I take g at x, put it in for x and f at x, I get back this. Can anybody think of another example? Anybody else? Kevin, do you have any ideas? Doesn't have to be complicated, right? Like as simple as you want it to be. What do you think? Caleb, what do you think?
Maybe like x cubed plus 1, and then for g of x would be just absolute of x.
Is that backwards though? Yeah. So x, but very good. X cubed plus 1, still want that to be there. And then absolute value of x. So I take g at x, put it in. Good. Yeah. Right? Pretty straightforward. Okay, next one. This would be a cheating one. I think you wouldn't. Sorry, I'm going back to A. You can finish writing that down, but this would be a cheating one. You could. This would always work. So you wouldn't really be allowed to do this on a test. But what if you did something like this? F at x equals x. G at x equals a function. But you can't just reuse the function, right? But that would always work, obviously. But if there was a case where you could do that, but make it a little bit more complicated, like if it was 3x or something, then you would get away with it. But you can't just use one of them. Can't be x. Okay, so B. Somebody want to try B? Go for it. And this is G at f of x. So you just got to put them in backwards. But yeah, Vivian, go for it.
G of x is like x squared minus 5, and then f of x is x plus 3.
Nice. Okay. I could think of another one. Let's say G at x equals x minus 2. F at x equals x plus 3 squared minus 3. Yeah, not minus 2 minus 3. It's just negative 5. So just put them in there. Simple in a way, right? But yeah. Okay. Next one. I think there's an obvious. Fog. Fog and Goth. So you have to think about the order that it's given. F circle G or G circle F. And I think it's a really nice challenge for the thinking involved. You come up with an easy one. Everybody's going to come up with this one. So f at x is 2x minus 1. G at x is 5x. Right? The easy one. Can you come up with another? Challenge yourself a little bit. You don't even have to write it down. But as you're doing your homework, like, try to think of a second one. Anybody come up with another one? How about this? 2 to the 2x minus 1. And then g at x is 5 over 2x. I put it in, I just multiply, and I end up with 5x out. Anybody think of another one?
Could you just flip it? So that would be, instead of 2x up there, it'd be 5 over 2.
Yeah. Yes, certainly. Yep, absolutely. What about this? F at x equals x minus 1. G at x equals 2 to the 5x. Okay. Last one. Everybody try to come up with at least one on their own. There's all different kinds here. I'm going to ask for everybody's, so make sure you come up with one. I'm going to ask you for it.
Don't put a couple in case somebody takes
No, if somebody takes yours, that's okay. But I want you to have something written down. You don't have to have. You don't have to have one that's unique, but you have to have one. Imagine if the whole class was here and I said everybody had to come up with one.
They're gonna listen to the video when you say that.
Yeah. Those skippers.
Everyone come to class when if there was a different one.
Yeah, with a different one. That's good. All right. Taylor, you want to start? Doesn't have to be complicated. Like, they're not trying to make it fancy. Make it easy. Just.
What if it's also not right?
Yeah, that's it.
F of x equals
Negative 2 log of x.
g of x equals
2x plus 2. Awesome. Who else had that one? All right. Okay. You're off the hook. Okay, go for it. What was yours?
The same f, but g of x was 2 bracket x plus 1.
Oh, okay. Can I change? Okay. So negative 2 log of x, g at x equals 2 bracket x plus 1. Good? Cad?
Mine says -2 log 2x, and then
Ah,
g of x
negative 2 log 2x. Good.
would be x plus 2.
Like it? X plus 1?
Or yeah, 1.
Yeah. Let me expand. Yes, very good. So similar, but slightly different. Kevin? Nice. Nice. Those are all the ones that I was thinking of. So great job. I love it. I don't have to do any extras. Okay, there's your practice.